Hey guys, welcome back. We got day 22. We're going to talk about electronegativity and polarity. All right. And so we're going to talk about polarity of molecules now, or polarity of bonds. All right. Polarity of bonds. So is a bond polar or not? So first, let's define electronegativity. Right. And that is the ability of an atom to attract electrons to itself. So how, right? I mean, again, human behavior, not the same as electron behavior, but we all have friends and we all go to some people's houses more than we go to other people's houses, right? Maybe you are the host or the hostess, and maybe you're never the host or the hostess, all right? And that's okay. I'm not picking on any, but there are some people who draw more people to themselves than others, right? In chemistry, they have it ranked by atoms. So the type of atom, right, depends on how much they attract electrons to themselves, especially in a bond, right? The top five are number one. So number one is fluorine, 2 is oxygen, 3 is chlorine, 4 is nitrogen, 5 is bromine. Now, if you look at nitrogen and chlorine, all right, our book, they're really similar to the same electronegativity value, all right? Actually, nitrogen and bromine, our book has them as the same value. Chlorine is big compared to the rest of oxygen and nitrogen, so there's a little bit differences with there. All right. Okay, and so a polar bond is an uneven distribution of electron density between the two bottom atoms. All right, and so what do I mean by that? If I have atom A, all right, so here's atom A. Doesn't matter what A is. And atom B. All right, and atom B. The bond is in between them. We draw a bond between them, right? However, the electrons aren't just a pair of electrons sitting there. That's not what happens, right? We call electron density between the two atoms. Okay? All right? There's an electron density because the electrons are not static. They're dynamic. They're moving around. And if this is a top 5, and so if B, right, if B here is one of the top 5, right, the electrons are going to spend more time over here on B than to A. Now, they still exist towards A, but you can, right, but they spend more time around B. All right, and so that leads to an uneven distribution. The bond, like if this was a good example, is if this was like a barbell. If you had a barbell and you had weights, you'd have a big weight over here and a little weight over there. All right, it'd be uneven bar. All right, if you're in the gym. Okay, or a desk that's got drawers on one side, not the other, right? It's the center of gravity is off center, right? So instead of the center of gravity being right in the middle, it's actually more over here. Okay, and so what we do for that is we write a delta plus and a delta minus if B is a top 5. Okay, because the electrons are not distributed evenly. Okay, so it's a partial charge. All right, not a full charge, but a partial charge. Now, we'll get to polar molecules, and a polar molecule has a net dipole moment, which means they have the overall charge on the molecule, the overall distribution of electron density on the molecule is uneven. So there's 2 poles of charge, right? Now there's slight poles of charge, not like full-on charge, positive, +1, -1, but there is a uneven distribution of electron density. We'll get to that later. Right now we're just talking about polar bonds, right? And Linus Pauling came up with the schedule or the scale, and fluorine is number 1, oxygen's 2, chlorine 3, 4, 5, and it goes from fluorine down to francium. All right, that's your trends. Now, it's a trend, and not everything follows the trend perfectly, okay? But that's the trend, all right? And of course, we have the stairs here. All right? And the electronegativity difference tells us what type of bond it is, all right? So when we have two atoms, their difference in electronegativity tells us the type of bond, all right? And I'm going to draw it this way. If I had a that's an arrow. We don't want an arrow. There we go. If we had a continuum of bond types, right? Right. And down here is the delta En, the electronegativity difference. 0 to 0.49, this would be the covalent. All right, okay, and equally shared in that range. So some examples, F2 to CH. Those are all equally shared. So, right, that's an equally shared. Then we have from 0.49 to about 2, like 1.9 here. We'll call it 1.99 because then 2 becomes something else. So this would be the polar bonds. And then over 2 is ionic bonds. Right, like NaCl is over here, cesium fluoride's over there. I have, HF is here, OH is in here, all right, NH is over here, right? So there's different levels of polarity, okay? So how do I tell? We're going to simplify this for you guys. If I have any two nonmetals, X bonded to Y, it's going to be a nonpolar bond. If I have X bonded to a top 5, polar bond. And if I have a metal plus a nonmetal, it's going to be ionic. So we're going to simplify it, just like we had, right? So if I scroll back up slowly to the stairs here, if we're on opposite side of the stairs, so anything over here and anything over here, ionic. These are the top 5, right there. Okay, so if I have selenium and sulfur bonded, phosphorus and sulfur bonded, carbon and phosphorus, carbon and hydrogen, doesn't matter. Those are all going to be nonpolar. I don't even care what the delta En is. All right. If I have nitrogen bonded to carbon, it's going to be polar. If I have oxygen bonded to carbon, polar. If I have oxygen bonded to fluorine, it's going to be polar. Okay. So when the top 5 are involved, as long as it's not the same, right? Oxygen bonded to oxygen, well, it's the same element. It's the delta En is 0. I do expect you to know that. But as long as, so O bond to O, non-polar, but O bond to any other one of these, we're going to call it polar. All right? Even if delta En isn't quite there, right? There's other things going on, all right, and that we don't get to talk about yet. So that we are going to oversimplify this, which is going to be perfect for us. If you have nonmetals, no top 5, it's a nonpolar bond. If you have a top 5 bonded to anything else besides itself, it's a polar bond. And then if we have a metal and ionic and a nonmetal, it's going to be ionic. All right? So not much has changed except for just this middle. Okay? And then with polarity, a good analogy to polarity is like, so technically right here we're polar and right here we're polar. But that's a big difference, right? Just like speeding. Right? The road behind my office is a 45-mile-an-hour road. If you go 46 miles an hour in a 45, you're technically speeding. Now, chances of you getting a ticket for that, as long as nothing else is going on, is very low. right? There's a certain point in time, though, where you're going to get a ticket and you're speeding, right? So if you're going 55, 60 on there, you're speeding, you're going to get pulled over, get a ticket. If you're going 70 or more, you're probably going to get more than a ticket, right? And so, you can be speeding and you can be really speeding and you can be recklessly driving, right? It's just kind of the same thing with, as an analogy. You can be slightly polar, barely polar, you can be polar, extremely polar, or you can be ionic, right? And so it's just basically how much do we share electrons, right? So we equally share covalent, we partially share at polar, and we don't share at all at ionic as electron transfer. So those are the types of bonds. And they have different properties because of how that happens. All right, so let's do some examples. Which molecules have a polar bond? All right, now I'm going to draw the Lewis structures just for practice because why not? Okay, do you have to draw the Lewis structures to do this? No, but maybe right now for us it's a good idea. First thing we do is valence electrons. So H has one valence electron, so one electron. And one electron is 2 electrons. So H2 is pretty straightforward. HH, I have a bond. And then, is that evenly shared? Yes, there's delta En is 0, right? Delta En is 0. And how do I know that? It's the same element. So if it's the same element, I do expect you to know that. Right? So this would be nonpolar. How about not? HF. Right away, right? I'm just going to highlight my top 5s. All right? Just going to highlight them. And so we have 1 electron plus 7 electrons to get 8 electrons. And so I have H and F. Boom. 2. 4, 6, 8. I have a polar bond. All right. Why? Because I got the top 5. Fluorine's the top 5. And so that I got a polar bond. F2, we have 2 times 7 electrons, so 14 electrons. 2 fluorines. F and F. 2, 4, 6, 8, 10, 12, 14. Well, delta En here is 0. Right? Same element, even though they're top 5s. Right? So this is not polar, not a polar bond. Not a polar bond. Water. 2 times 1 electron plus 6 electrons. Right? So that's total 8 valence electrons. HOH. 2, 4, 6, 8. We have 2 polar bonds. All right? Because O is the top 5. And then carbon tetrachloride. We have 4 electrons for carbon, right? And again, I'm getting this from the periodic table. So if you need to review the valence electrons, feel free to do so. But 4 electrons for carbon plus 4 times 7 electrons, all right, for chlorine. So that's 32 electrons. Carbon's in the middle. 4 Cls. And chlorine's the top 5, so I have 4 polar bonds. Fill in the octets. So that's 8. That's another 8. That's another 8. And that's another 8 to get to 32. So we have 4 polar bonds. Now, 3 of the molecules have polar bonds. That one, that one, that one. However, only 2 of the molecules are actually polar. And we'll get to that why, because it's more than just the electronegativity difference. There's also the shape of the molecule does play a role. And we're going to learn shapes soon. Not yet, but soon. All right. Next up, your book does these two things. All right. And so I'm not big on doing this in Chem 1. Your book covers it, so we're gonna cover it. What the dipole moment is. All right. It's actually calculatable, and we like being calculatable. All right. It's a product of the charge and the distance between the charges. So mu is the dipole moment, which in the bis, right? And Q is the charge, R is the distance. All right. There are some worked examples in your book for this, same as percent ionic character. And percent ionic character, and it's for a reason it dropped down below on the next page. But your percent ionic character is your observed dipole moment over the calculated dipole moment times 100%. This should be extended here. Okay. And because the observed is not always the same as calculated. So that's calculating dipole moments and percent ionic character. All right. And that's all we're doing for electronegativity and polarity. Is it polar? Is it not polar? All right. All right. Does it have polar bonds? Does it not have polar bonds? In the next video, we're going to talk about some exceptions to the octet rule. All right. And so let me know if you have any questions, and we'll see you next time, guys. Take care.